And welcome back for the last time during this spring for the software maintenance course and its lectures. This is the last lecture of the series. We will have one event which will be about what we had on this course as topics and also talk about what will be going on the exam. But this week we will still have the one last topic to discuss about the software maintenance. So, uh, like I said, this course is now wrapping up, and we are on the last legs of these presentations and discussions. Next week we will have a visiting lecture, or we have a time slot for visiting lecturer. Unfortunately, at this hour, we are going to replace that visitor with a video lecture by someone else about the agile process models and how they actually function in real life. But we have a reservation or reserve time slot with the uh, summary lecture. So let's see if that would work better. But anyway, let's start with the content of this week. And like always, we start with a quick recap on what we did last week. So last week we talked about software aging and how these software aging and the software age actually affects the software maintenance and what are the main reasons of why software gains age, even though everything in the computer side of the system is more or less mathematic formulas and instruction sets, which themselves do not actually change at all during their life cycle. Anyway, it is established that programs do age. Like anything else, they are constructed by humans and they exist to provide us service. Of course, the needs and the requirements of these services and products change a bit during their existence. So to answer to these problems or to cater to the new expectations of new users, the softwares tend to change a bit during their existence, and this is also what causes the programs to age. On the introductory stage, we emphasize the user support. On the growth stage, we emphasize the correcting the faults which still exist in the product. And on the maturity phase, we emphasize on the enhancements to keep the system alive. And finally, on the decline, we emphasize on the technology changes to keep the system relevant on new newer modern platforms if the system still warrants a need to actually keep it existing. On this topic, we also had another set of slides about how industry should react to the different types of legacy software. For example, if something is of low quality and of low business value, these things should simply be thrown away because there's really no use for them. Or we could also replace the existing specialist system with the commodity off-the-shelf tools. If we have existing system which is of low quality, but we still have high business value for it. Or finally, if we have high business value and high quality, we try to extend the life cycle of the product by doing maintenance cycles. On some other aspects, if the business value is not that much, we might have to consider some other approaches. But basically, we have a number of strategies to cope with the software maintenance needs of aging legacy systems. Anyway, this actually doesn't have anything or does only have some fringe areas related to this week's topic. So we have been talking about for the last 9 weeks about the different aspects or different concepts which are related to software maintenance standards and software maintenance in general and software maintenance in real life and these sort of things. For example, test automation and what sort of cost structure there are, what are costly activities, what sort of skills do we need to have, what sort of tools we need to have. So on this lecture, the idea is that we talked about these things or software maintenance from the research point of view. So what type of things do we do in academic research, or what sort of theory there is behind studying software maintenance? First of all, of course, one of the most famous things in software maintenance research are the Lehman's laws on what happens and how all software products and services live. There's a number of laws which more or less are true in all the scenarios. For example, the first law is the continuing change, that the system will become progressively less satisfying to its users unless continually made changes to meet new needs are done. Also, that the product increases in complexity, or that the self-regulation law, third law, that the process of software evolution is self-regulating with respect to the distribution of the products and process artifacts that are produced. Also, finally, something like the conservation of organizational stability. These are the first four of them. And if we continue with the other laws, there's a conservation of familiarity, meaning that you should, or you almost always keep some parts which are familiar to the user so that they don't have to relearn to use the software, or that the new content is something that's somehow familiar. Also continuous growth, so the system should keep growing in order to please its users. I know that, for example, some things like, for example, Windows phones did downgrade patches, which simply removed services. But considering how successful the Windows Phone in general was, this obviously shows that you have to keep offering new things, not just take away stuff. That's rude. So don't be that person who does that. Also, something like that the quality keeps declining because, like mentioned earlier in the last lecture, it's not that the system itself decays, but if we don't do anything, the customer expectations shift, and then we are behind, and the quality declines because the users perceive it as of a lesser quality than something that was designed with the today's ideas and ideals in the mind. Finally, the feedback system, the eighth law, that you really should have a system to collect feedback from different levels, from different users, from different stages to make successful software evolution cycles. Of course, these things summarize more or less the things that we already have been talking and more or less know already about everything, but still they are something that's more or less research things and more or less hold true in all the different scenarios and all the different types of software projects. So this is something that was mentioned on the very first lecture. So why do we study maintenance? Why do we do research in this area? Why do we actually are even interested in this aspect? Shouldn't the University of Technology be interested in modern things, new things, things that don't exist yet, or novel aspects? But on the other hand, we are going towards a world where everything is software. Everything, every industry is basically software development. We are just making also different hardware platforms on which we run our software, and that hardware does its thing for the other stuff. For example, in a sawmill industry, you really can't run a sawmill or timber yard without having a software, because the tool automation already exists and the smart tools require programming work. Also, something simple like a truck lift or a jack lift requires software, because everything inside in its hydraulics, for example, is probably run by embedded software, which was made by programmer. And there's no longer dedicated circuit boards which run things on hardware-based logistics. There's a processor which runs the sensor network and gives the instructions to the actuators to do their thing. So basically what I'm saying is that we are constantly moving towards software, and also because we are doing that, we need to understand how to maintain software aspects of different things. This is also obviously something that I have been talking about throughout this course, that we need to think software products as a sort of a product line things, or we should, because the software products are in a situation where their life cycles are maybe even tens of years, and we might be in a situation where we need to tailor the existing core for the new products, just like in an automotive industry. Well, anyway, uh, considering that why we should study maintenance from the viewpoint of software engineering. The maintenance is the major share of software lifecycle in most types of software things. That's just a fact of life. So of course we need to understand how the software evolves, how it's maintained, what sort of tools we need, what sort of problems we have, and these sort of aspects. So of course, we need to understand the problems so that we can put maintenance effort on to fix the problems. And of course, if we want to upgrade something, we should also be aware of things that might happen or have a strategy on how to, for example, replace the legacy things or understand if that legacy system is even worthwhile to replace. So, why study maintenance? Well, software maintenance may be a significant portion of lifecycle costs. It's basically always this. There's sometimes you can say that some products are that you really exist in a world where you release it once and then don't fix it at all. These things usually are a really small subset of all software, and usually related to something that's not that's fairly lightweight in their usage. They don't have a real long-term usage, or they don't really have high criticality activities. So also, some software maintenance and software maintainers also use number of specific tools, methods, and techniques. Of course, the tools themselves are more or less the development tools, which probably are used also by the people who make the software. But the long-term effects of something like documentation or the suitability of the tools or the compatibility of the framework towards the new technology isn't something that's obvious to people who only deal with the cutting-edge software development. These people might not actually understand all these different aspects, and they might not actually have a clear understanding on what is needed to keep software maintainable throughout the years. So this of course means that the software maintenance actually has its own tacit knowledge, which also means that it's an area that you need to gain experience in, and finally a thing where you have to learn stuff. So of course, combining this with the idea that all types of software built with whatever technology, technique, or tool, or for whatever use, also need maintenance probably at some point of their life, if nothing for nothing else than for the tailoring process of using the code base on the next project. It's actually fairly interesting to see that the software maintenance isn't actually considered that hot topic for a software research. Actually, there's studies which say that 93% of all product costs are generated by maintenance phase of the life cycles. Of course, this also means that there's bound to be development after launch. And for example, in mobile games, this is completely normal thing. You launch the core, see if it attracts people, and then offer longer support for the things that and for the product if you have the necessary number of people who are still interested in it. And in fact, there's a rule of thumb here. This is also something that the economists or marketing people keep saying, but it kind of holds true also, although I think it's a bit too universalist, saying that it costs €1 to come up with an idea and proof of concept, €10 to test and develop a product, and €100 to maintain and commercially support the product through its life cycle. Of course, indicating that about 90% of the costs are generated during the maintenance and not development. But of course, after this course, you also understand that maintenance is not just maintenance, as in a sense with a car, changing oils, changing spare parts for something that gets broken, but it's also actually fairly active development, of course, with some limitations on the types of products and what we are actually doing with the software. So, on the standardization, the software development processes are fairly well standardized and certified. There's IEEE and ISO, which both have a number of different definitions on how the software how the software development and maintenance should happen. There's also definitions for software lifecycle processes and different aspects of how software should be developed, documented, maintained, how problem identification happens, how we do requirements analysis, how we do architectural design, implementation, what sort of things should be done with the software testing activities or quality assurance steps. Actually, for this, there's even a large standardization which gives you the basic measurements and these sort of things. Also, how to develop software with the iterative processes and all the other things actually means that there's a wealth of different ways to formally define how software is developed. Also adding into this all the different certification processes, for example, ISTQB for software testing, or different company certificates, something that, for example, Microsoft Academy offers, means that there's a wealth of different formal ways of defining and describing how we should be doing things. Of course, this is a sort of research into software maintenance and software development, because it also means that there's a book or a formal way of learning things, and also that there's at least some experience-based knowledge codified into these standards or certificates, or at least we hope that there is. If it's completely written on the fly by someone who has never been doing anything, it's of course a troubling situation. But with the IEEE and ISO, IEC, there's a sort of hope that at least their processes mean that only things that we can agree upon and things that we know to be true are included in the standardization. Of course, there's some ridge areas also on this, but in general, the standardization is fairly well researched, or at least based on the de facto practices of the industry. So, the software maintenance has its own process models, and it has its own activities, and it has its reason to exist. Of course, if we consider this from the larger perspective of software engineering, there's actually two views on software engineering. There's the one part which says that the software development or software engineering defines the software as a technical artifact. So we define the structural qualities of the software and the qualities of the software development tools and the requirements of the tools of the software and what it should do and how we should uh, check or validate that the software does what it's required to do and provides correct output. This is the idea of the definition of the software as a technical artifact. It transforms inputs into outputs defined by the requirements. Of course, we know that this is not all about software development. There's the other view of software engineering, and it means that it's the software development as an industrial activity. So not only are we making an artifact, in this case software, we also involve the development process, or the human factors and the human organization, and the practical usability and applicability of the tools and their problems, and all the other things which affect how the software should be made, how it should be documented, how the version control thing happens, how human factors affect the thing. So of course, this is the other view of software engineering, and in fact there's an IEEE definition that the software engineering is an application of systematic, disciplined, quantifiable approach to develop, operate, and maintain software. Of course, this means that, wow, software engineering actually is also about software maintenance. In fact, if we take a look into the different areas of software development, which are defined to be areas the software engineering and software development is actually interested in. Of course, there's business management, there's quality systems, project management, requirement specification, architecture, design, programming, testing, deployment, maintenance, product management, quality assurance, testing, documentation, and requirements management. These are just a number of different things. This also skips largely about the soft factors of software development. But anyway, all these things, they have, of course, some area which affects everything. And in fact, if we take a closer look, the maintenance is defined here. Okay, so maintenance is changes to the software after the deployment. This is fairly simplistic thing. But of course, knowing that the software maintenance cycles or development cycles during maintenance actually are sort of mini projects about on the software while it's in maintenance. Of course, we need to do testing work, we need to do quality assurance work, we need to do design work, we need to consider architecture, we need to do programming work, and so on and so on. So, in fact, if we consider what do we do in the software maintenance, we actually do everything of these things. So not only are we doing the maintenance thing, which was by the namesake, but actually in the maintenance phase, we are actually doing all these things. So there's no reason to say that we don't take one part into account while we are in maintenance, especially if we compare it to the stage when we are doing just development of the first version. The only difference is that the first deployment hasn't happened yet, so we don't have real-time, real user data to use as a quality assurance tool. In fact, this also for this lecture means that instead of talking about the research of software maintenance, we actually should talk about research of software engineering, because software engineering includes software maintenance, and software maintenance includes all the aspects of software engineering work. So the rest of the lecture, of course, goes from the perspective of just software maintenance to more generic to the perspective of the entire software engineering. So there has been several things that have been proposed in software engineering discipline as silver bullets throughout the years. Of course, the silver bullet being the thing that fixes all our problems. And for example, the Conradi here has defined a list of things that we have been doing and what sort of things have worked. So software reuse using the commercial hardware tools, focusing on the software development aspect, not hardware development. Of course, that works. Formal inspections work. Systematic testing works. Documentation practices, making them better works. Version control systems work. Object-oriented programming works. High-level languages work. Or, well, of course, we still have to do something that's not really high level. And of course, having more dedicated people who have been taught or to use their skills or develop their skills towards software engineering practices or tutored to become software engineers when they graduate. So of course, we have a huge number of silver bullets throughout the years, but still we are having the same problem. So of course, this means that our silver bullets are not enough or not silvery enough. So then we add more bullets to the gun. This is how Americans do it, so why don't we also try to do something similar? Well, these things are more or less probably works. So we should have better education. But how do we do that? We probably have to use UML to visualize our ideas. Of course, this needs some sort of approaches or process models which actually allow or emphasize or at least use the UML somehow. It doesn't have to be the rational unified process. In fact, the original idea of using UML as a visual programming tool was a complete failure, but the UML lived on because it was a fairly good idea on how to visualize program or how to make a visual presentation of an idea which doesn't exist yet. For this is the UML works just fine. So also, do we have powerful computer assisted tools? We have been talking about these things for years, but not much has surfaced. Of course, the current tools are better than the earlier ones. They offer more assisted features, but they still really are not that good. Of course, do we use agile methods or incremental methods? Well, of course, that also works, at least on some projects and some types of development work, even though they are creeping into almost all the different types of projects, but still, it's something that made the overhead more bearable. Also, do we do software process improvement? Well, we have different models, but we know that the industry isn't very keen on these things because they all cause risks and are not that much used in real life. Structured programming, well, I don't know how that would help or how useful that is. Code generation, formal specifications, verifications, they have ideas, but for example, the code generation thing doesn't scale up that well. Or if it scales up in a sense that it is able to give you a framework to work with based on your ideas and documentations, then at least it needs to be optimized and fixed. So of course, what it means is that we have a number of silver bullets. They have helped, but we are not there yet. So we need to move more development or more research into these areas to understand how we could enhance the software engineering development and maintenance practices or provide better tools. For example, one of the current trends right now is create artificial intelligence based smart tools which try to assist the user or at least pinpoint problematic areas which probably are lossy or badly optimized or which follow patterns which we know to be problematic or difficult or prone to errors. So we don't have the silver bullet yet, or we have several silver bullets. We don't just have the one that fixes everything. So how do we do things? Of course, there's one area in particular, which, for example, also Lund University Software Engineering Group tends to use quite much, and it's called empirical software engineering. So, the empirical software engineering starts by uh, understanding that the software engineering is a bit of a special case. There's a couple of problems which make things difficult. And this basically stems from the fact that the software doesn't have size limitations or weight limitations or realistic limitations besides what you can compile, you can use. If we are building a bridge, for example, if it doesn't if it doesn't hold the 100 tons of steel which is used to test that it actually is stable enough, then it's a bad bridge and it will never be used. Whereas on the software side, you can make a complete crap of software and still it might end up being used because after all, it just does something and we don't have money to fix that. Whereas if we were building bridges with the same idea, I would probably be swimming across the rivers because I couldn't use the bridge or trust them at all. Also, in a sense, even though we are trying to serialize the software engineering development, most of the software engineering projects in the industry are sort of unique. They have their own goals, they have their own technology requirements, they have their own people. So the reuse, while being considered very good practice, isn't always available. There's also the fact that there's a fast change rate between the projects, meaning that there's no long-term stability. The technology keeps changing, which of course is one of the problems of the software maintenance people. But still, there's no long-term stability in the area yet, because the technology isn't, or at least wasn't, in the point where there's really no new innovation or where we can really rely on the fact that when we make this once properly, then we don't have to fix it for the next 50 years. Also, this means that the change rate inside the projects are also huge because the requirements keep changing and there's much improvisation. And finally, because we are still living in a sort of hectic approach where the platform keeps changing throughout the years, like I mentioned as an example, in the nuclear power plants in the United States, the standardized computer system managing all the automated valves and automated production lines is something that has been stable for the last 40 years. And I think that if we are building something out of reinforced steel, the reinforced steel hasn't really changed that much throughout the years. If we discount the fact that once we started to do atom bomb testing on the atmosphere, we kind of ruined our steel for the purposes of using them for measuring highly sensitive stuff. So that's obviously one change, but doesn't really affect the use of steel in a sense. Also, because we are living in a sort of hectic world, there's really not that much time to be properly scientific. So building theory, hypothesis, you collecting metrics, doing data analysis and these sort of things. We just keep doing it on the fly. Also, not from the engineering point of view, the software engineering is really soft. We have humans, we have organizations, we have to take into account that people make errors. People might not have that good knowledge or background or experience on all the necessary aspects simply because we can draw or do programming work and create some horrible shitty programs, and it's fine. But if you are a bad architect or you really can't draw or design a bridge, then you probably won't be an architect for a very long time. Whereas in a software engineering, this is not a problem. Also in software engineering, we really quickly achieve situations where we actually have more variables than a space shuttle, so we almost always have to rely on other people doing their job properly, and there's no easy way to see or test that everything is done correctly. For example, with concrete blocks or steel, there's really simple measurements to see if it's hard enough or if it's bouncy enough or whatever. So but there's really not those things for software engineering. Also, these all are things that we need to overcome when we are trying to understand or trying to collect information on software and development work or maintenance work and try to make the world a better place by making new ways of developing software. Of course, this endless cycle might never end. Uh, at least not until artificial intelligence makes everything and super optimizes everything based on someone telling the system what we want. But but we need progress, we need development, we need to do new things. For example, throughout my career, the agile processes started up as being a fever dream of a couple of really crazy guys, and now they are more or less become the standard of software development. Not only because the models themselves matured a bit, but also because the computers became so common and software development became so normal activity for people that the huge piles of documentation, for example, developed by NASA or the Soviet Union Space Agency or whatever it's called, uh, it's not worthwhile to make all that from today's software development. So some guys said that, hey, there's a way to do this with more lean approach where we don't focus that much on documentation. Of course, the first guy said that this is a crazy idea. How do we know how to fix things? But the agile people understood and were adamant that when we have enough software development, the need for different types of software, there will always be replacements. So you don't have to super detailed documentation on absolutely everything that has ever happened. So the empirical software engineering tries to do work on developing the software engineering practices. So of course you will have a separate course on research work. So we are not going to go too much into the details here on this lecture, also because we have already used 40 minutes of it. But for example, the normal types of software engineering research on the empirical side is doing some of these approaches. So we might consider some philosophical discussions or do literature reviews or create proof of concepts or prototypes to get an idea that how some technology might work or how something could be done, or do design science or mathematically model things, or if we are talking about something really small scale like algorithm optimization, we might even do actually mathematical proofs, but of course this doesn't scale up to larger environments, or even do simulations to understand or test out that our system actually works. There's also benchmarking approach, or we just do testing work, or use grounded theory approach, or participative preparations, doing workshop with the people to understand the problems and enhancement proposals and ideas, and identify the current existing problematic phenomenon which we need to get rid of to get the process more fluent, or do action research, in which the researcher actually participates on the development activities trying to make the system more usable, or field study, or case study, or structured interviews to collect structured information which we can then apply grounded theory approach later, or even use survey approach to analyze the structured interview results. Or do post-mortem analysis or do a real phone survey or online survey or do data mining approaches on the existing archives of bugs and documentation and what things we have been doing, and even controlled experiments or experiments in general, either in industry in vivo or among students in vitro. Means that in vitro means that in lab, and in vivo in live. So of course, or in vitro actually means in a petri dish, but let's not focus on that too much. But so basically, there's a wealth of different approaches for doing software engineering research. And this also means that if we are talking about what software engineering or software maintenance researcher does and how he does it, or she does it, or what sort of approaches they use, well, actually, unfortunately, the answer most likely is going to be all of them, because there's so many different aspects and areas of software development that there's no way of saying which one of them is the correct or the right or the most traditional one. We might have a busload of software engineering researchers and none of them actually do anything which is even remotely close to something that other one does. And they are all legit software engineering researchers. So of course, in this sense, it also means that if you want to become a software engineer and software engineering researcher, you will, of course, in university research, focus on one area, couple of methods, couple of things that you want to achieve in your research project. But in general, you are much better off as a generalist who understands how different approaches work, at least more than being really good at one small thing which is not always applicable. Of course, we also need those super professionals, but still, if we want to do industry research, want to understand how the processes in general happen, or want to include all the soft aspects of software engineering into our work, we need to have more generalist approach to have different options available for different situations. So there's a couple of slides here talking about the different ways of doing software development, software engineering research, and empirical software engineering. So basically, it's a scientific use of quantitative and qualitative data to understand and improve software products and software development processes. This is really good explanation. It summarizes everything. Unfortunately, it's a sort of vague, like I mentioned, because the software engineering researchers do very different things. Okay, so, but in any case, how we do it is that we collect data, and we collect data to understand, address our research question, do validate the results, do some analysis on how probable it is that the results are correct, and then publish something trying to make a small step towards better software development or software engineering practices. So, of course, we really can't use anecdotal evidence or common sense, like, well, in any real research or engineering field doesn't also accept them. So we need to have measurements, we need to have evidence, we need to systematically gather the evidence, we need to get them from as wide perspective as possible, and then we need to do the analysis in a proper way to show everyone that our chain of evidence and chain of logic actually provides the necessary results we are trying to show here. For example, if we are doing grounded theory, we might focus on one organization to understand its problems, but we can't say that the ways to solve their problems are universal in any way. Also, unfortunately, even if we observe 10 organizations and find a way to solve their problems, we still can't say that it's universally applicable, because those 10 organizations might be the only organizations in the world which have these problems. So with the gathering of the evidence and understanding what happens, it's also really important to understand the scope and generalizability of what we can do. And of course, because we are talking about wildly different things, there's basically the in vivo versus vitro, the in the lab versus in the wild, or qualitative versus quantitative studies, or the meaning that we are having a few quality measurements or number of statistical measurements, or we are doing primary studies versus secondary studies. So we are directly affecting things or directly observing things, or we are using the secondary source of work. So basically, there's a wildly different scales here. So of course, in the lab versus in the wild means that there's a couple of different things that we can do. For example, the in the lab includes things like controlled experiments, and in our case, usually literature reviews, where we are just observing what has been done, what is already proven, how can we use this information. And on the in the wild approach, we do case studies, we do action research, we do grounded theory, we do surveys to understand how the organizations are doing things or how some new technology might be used in some real life organization or in real life product or real life service. Finally, of course, when we are doing the data analysis, we have collected information, for example, from the testing practices or the testing resources allocated to different types of development places. We can do large scale analysis, we can do small scale analysis, qualitative analysis, quantitative analysis. But in any case, there's different ways of completing this step on the different research approaches. And for example, here, unfortunately, the picture is in Finnish, but it's about how organizations divide or allocate their quality assurance and testing work resources. So of course, like mentioned earlier, it's fairly infuriating that in most occasions things are related to the hardware, to the tools, to the people, to all these different things. So it's not very surprising that, for example, the testing resources are why they exist, what sort of things they are, what sort of things are related to each other, actually forms a huge network on which we also can identify different problems or enhancement proposals or other things on how to better use your quality assurance resources or what sort of problems there are in your resources. Of course, you can't see if you can't understand Finnish, you don't see, but on the right hand side of this, on the middle on this diagram, there's a problem tools which is associated to the amount of tools. Of course, this is fairly straightforward observation, but some organizations actually kept complaining that their people are just sitting around, thumb up their nose, because they don't have enough licenses for their test simulation software. So, of course, whether it's a resource problem of money or just oversight of the management, it doesn't matter here, because the problem is that they have the right tools, they just don't have enough of them to give them to each worker. And of course, this isn't a generalizable problem, because this doesn't affect all organizations, but it's at least one thing that you should be aware of if you are running an organization which is doing your business's testing work, to see that it's at least theoretical possible to put every tester to work at the same time, because of course this is something that you would expect, but when we go into the wild, we see that this is actually something that isn't actually done everywhere. Also, on some occasions, there's another problem on the left side, on the upper part, the distribution of the resources, meaning that there are some projects which are having more than they need because they are just thrown people because it's considered so important, whereas other projects are lacking people and lacking time and lacking money or other things, even if there are no really good reasons why this happens. So of course, these sort of things. So going a bit more abstract into the abstraction of software engineering research, I decided that I'll close this lecture with some ideas from Malavolta and Czernokovic, which both are also software engineering researchers and have provided a fairly interesting set of things to consider, especially if you are considering going from these master's theses to doctoral studies and what sort of things to think. First of all, what makes a good research? Is it hard? Is it useful? Is it elegant? If these all are true, then it's probably something that's really worthwhile to study. Of course, not everything is always useful, elegant, and sufficiently hard that the answer isn't trivial. But in any case, if you want to go to the software engineering research work, you might want to consider that these things, at least two of these things, should be somewhat good on your scale. It also means that you want to probably do something that's useful for the public, or something that generates new knowledge that's useful in some other way than just providing you with a dusty publication which no one reads because it talks about something that has no meaningful impact on the real world or real software development. So, of course, everything starts with a real world practical problem, and those are annoying because they need real world practical solution. So, of course, almost always there's three aspects. It has to be a functionally correct answer with the problem as well, the solution. It has to be something that's cost effective or costs is cheap enough to buy so that it's actually a solution that can fix things, and it has to arrive on time. So if we have all these three key objectives to a real world practical problem, then there's a good chance that we develop a real world practical solution, and that's actually something that we of course want to do. So there's an example here. For example, a weather application, but we will not pay too much attention to this because basically this is already knowledge that we know. We are developing a weather application, and we sort of want to create a software which sends you alarms and probably even helps you. So we collect information. We try to collect some information and understand how different applications work, and try not to make something that creates malware indicators and stuff like that. But anyway, considering that we had a real-world practical problem and we need a real-world practical solution, it's rarely easy to jump right in. We start our research by making an idealized problem, meaning that it's something that's a bit more simplified. The idea is that then we can approach it with a research technique, some method, or developing a model, system, proof of concept, and that solution provides something that solves the idealized problem. So we simplify the problem so that we can create by a means of research, something that creates a simplified solution. That's more or less always the research strategy, because real world has the annoying problem of having too many variables to be handled at once. This is also why the in vivo and in vitro division happens. We need to have something that works in the lab so that we can try it out later in the real world, if it still works or if it's something that needs more refinement. This is also why the researchers tend to have this fairly comically inept uh, in in people tend to view researchers as comically inept in real life situations because they are trying to propose solutions which never work. But of course, this is something that stems from the way the researchers approach most of the problems. We make a idealized problem, simplified problem, so that we can create a answer, and then we try to see if that answer actually works in a real world as a practical solution. So if we were making an app, well, these are something that we would be doing. We would try to understand our competition, try to understand the themes and the user APIs, and identify outliers and these sort of things. Then, when we have an idea, we try to, as a first validation task, when we have a research setting based on the idealized problem, we do research work and we have solution to the idealized problem in research setting. Then the first validation task is, of course, does the product solve the idealized problem? So can we solve our problem in the laboratory? And if it works, if it seems to fix everything, then we try the same thing in a real world. So we might do some additional refinement, but if the idea, which was the key point of the simplified or idealized solution, if we take that and put that on the real world and see how it works in a real world practical solution. And of course, so the validation task 2 would be that does the product help solve the practical problem? And if it does, then congratulations, you made very good research contribution. But usually in most academic research, we stop with the validation task 1 because we are able to solve something in lab, and then the real world practical problem and solving that, unfortunately, usually is more or less a private sector creating new products, services, and applications to do these things. And so it's a commercial work or done by someone else than university, because university only is more or less interested in the idealized problems and solving them, and then providing a feedback or background on which new products, patents, and these sort of things can be developed. But this is real life, and this is something that more or less happens everywhere. So you shouldn't really feel too bad about it. So of course, well, we need research questions. So we ask ourselves questions. Can our technique effectively identify anomalies, mismatches between description and behavior in Android applications? For this purpose, we manually inspected the top outliers as produced by our technique. Can our technique be used to identify malicious Android applications? For this purpose, we did something else. So in addition of actually making a study on weather applications, whether they actually provide you information and what they do, we developed a framework to understand how they could be malicious and do they have the necessary characteristics of doing something malicious, even though they are providing you at least some parts of the service, or how the weather applications should work and what they could do to be actually harming you or doing something nasty on the background. So of course this also means that we are always working on these 3 steps. We have research question, we have research results, and we have research validation. So we ask ourselves a question and try to understand, can this be done? Is this something that could be done? How could we measure something? How could we understand something? So on and so on. Then we provide the results of our research work, and then we try to validate and see if our solution works or if our model is correct or if our estimate is close enough. Of course, how we can prove that is also another research question, but it also means that the validation work provides us with new results, and new results provide us with new questions. And this is the way of life of research work. So this is something that you should also expect. So there's a number of different research questions: feasibility, characterization, method or means, generalization, discrimination. Uh, these are all valid research question topics. Also, if we are doing something with software architecture, then we can do some, for example, research on how the system is built, how it's designed, what sort of design patterns should we use, or is there actually software architecture somewhere, or does it exist, or how should it actually be, or how it's used in real life versus how it's defined in the laboratory. So there's really several ways in this, and there's actually a reference to a work which studies software architectures in practice. Also, if we take into an account of what sort of research questions can we make from software architecture using the previous categories, they are here. So there's really no limitation on what we want to study. Is it possible to automatically generate code from an architectural specification? What are the important concepts for modeling software architectures? How can we exploit domain knowledge to improve software development? What patterns capture and explain a significant set of architectural constructs? How can a designer make trade-off choices among architectural alternatives? So basically, if we can answer to all these different things, well, I think that's actually several doctoral dissertation works, but these all are legit questions, research questions about software architecture research. So this also means that we can study several aspects of the exact same thing even at the same time. Also, well, if we go to the research results from the research questions, we can have several different types of results. It's analytic models, empirical models, the system itself, qualitative and descriptive models, different types of techniques, a new way to do some task, including how implement things, embody result in a system, create an empirical predictive model. All these things are really valid research results. Or it's early architectural model, or architectural patterns or anti-patterns. Architectural definition languages, for example, the UML here is something that's actually mentioned on the slides, or ways to do formal specification, or communication metrics as indicator of how impactful some design decisions are. These are all really good results on software architecture. And finally, on the validation work. So we are trying to do this. We are trying to have a solution to a real world problem with a real world practical solution, and we are doing the validation work. So what sort of validation approaches can we have? Analysis work, experience-based approach, evaluation, implementation, persuasion. Implementation, well, here's a prototype that solves everything. That's a fairly good approach. Or experience-based, not so that we have been using this and it keeps giving us correct results, or we have system which predicts the same results than we get from the later real life calculations. So our model is actually useful and it can produce in practice similar data, and so on and so on. These are more or less related to the different ways or different objectives or the defined research project on what we are actually trying to achieve. There's all, well, what can we validate? There's a list of things here, but like mentioned, it's really about the project you are doing or the ideas you are trying to implement, or what sort of questions do you have, what sort of things that you are expected to do, what sort of construct you need to create to be able to show that this actually works, or what sort of constructs you are required to make that you can measure some phenomena and then try to get an idea on why it happens and how it happens and these sort of things. But they are all really about the type of research you are trying to do. But there are a couple of building blocks for research, meaning that there's a number of ways which will doom you to failure, but there's also a number of ways to do something that's probably going to provide you with a correct result. So there's a couple of models here. For example, if we have a question, can something be done better? And we build in our own alternative and measure them to each other. This is of course a good plan. This is really a common good plan. Can we enhance something and then we try to enhance it and see if it still works? Of course, there's a couple of other things. Can we do something at all? And then we build it and hey, it works. This is a very good plan. It's actually something that really works. Is X always true of U? Then we show that if we have U, Y, then we always have X. So that's also something that works. So of course these are just a couple of examples, but of course there's even if the software engineering research might be something that you might consider as a convolved mess, there's actually a couple of ways that are commonly considered feasible and commonly considered to provide useful results. So, but this can only be learned by actually doing or participating in the research work or participating in the development work, or at least understanding the domain enough that you can actually see or get an idea on how we should approach these different research problems so that we can formulate questions, so that we can collect data, so that we can actually validate the data and then start from there or continue from that. So, but there's still a couple of things that you really shouldn't expect as an engineer, software engineer. So, if you make a 10,000 line demonstration system, it might not or will not scale to a full-sized system. You are not always the person to have an absolute truth on how things should be done, and functional correctness is not enough. Even if the functional correctness is really important quality attribute, it's not sufficient quality attribute. You need to also focus on things like updatability, maintainability, how well it's optimized, for example, and other things. Functional correctness is not the only measurement. Of course, there usually isn't, and there almost always isn't a complete consistent specification. And even if there is, it will change when the people's expectations and requirements change. So you will never work with complete consistent specifications. Also, you don't just build things on software engineering. You will have to do tailoring work. You will have to learn new stuff. There's usually always something that has changed after you last time worked with things, and it really isn't bricklaying. You have to budget time to learn things, to fix things, to understand things, even though this is your 15th similar type of project. they all are unique in one way or another. And finally, even if we have something that works in a lab, it might not work in a wild. This is all something that I mentioned earlier in the design of games or mobile games in particular, that your designer's crazy idea, which is considered funny, might work on paper but not as a product. But on the other hand, some dull idea which doesn't sound very appealing might actually work very well with your customers. So you might not be able to devise a solution alone. You need to go to the world to see that it actually works. This is just how software engineering works. So, what to remember from this lecture? Well, the first thing to take home probably is that software maintenance doesn't exist in its own bubble. Software maintenance is part of software engineering, and software engineering has different things attached to it, mostly because it's a huge, sprawling area of things that you can actually do and still call yourself a software engineer. There were a couple of things or ways that software engineering is usually done, but this doesn't mean that you have to always follow these rigid rules. It's just that some approaches are inherently better than others, but there's no one way, method, approach, data collection type, research type, or thing or area to focus on which is inherently better than other similar areas. It's all fairly context relative, so whenever you are doing software engineering research, you should focus on what I'm actually trying to achieve, what I'm actually trying to solve, what sort of data can I get to understand how it happens, and how can I validate that I collected the correct data and fixed the correct problem. This is more or less the starting point of everything that's in software engineering and software maintenance research. So, like mentioned earlier, we don't have visiting lecturer next week because the person I was considering didn't have a suitable date. So we are including a tech talk by Dave Thomas, who is one of the Agile Manifesto pioneers, about agile process models in software development in real life. We are also have a reserve spot for the visiting lecturer. Let's see if we can have person by then. Anyway, next week we have this video lecture, and in 2 weeks we will start with the seminar presentations. And after 2 weeks of those seminar presentations, we will have the last meeting with the visitor or without, when I'm giving you a talk about the exams. So keep your eye on the Moodle pages for that. And finally, I want to remind you that you need to submit everything related to your weekly homework assignments and both projects before the 1st of April, 8 in the morning of Monday morning. And of course, this is Finnish time, not Hawaiian time or something stupid like that. And this deadline affects both projects for all teams, regardless of which seminar session your team presents in. So even if you are lucky and get a lottery position on the second week, you are still expected to turn in your report and your presentation slides before the first seminars, because the people who are presenting in the first seminar are randomly assigned during the seminar event itself. And of course, this means that your team has to be represented in both seminars on the 1st of April and 8th of April. And these seminar presentations will take place from 10 in the morning to 12 o'clock on the midday at the lecture hall 2209, which is the place where we started this course before we went to the online lectures. So your team has to be represented in both of these seminar events. There will be a list collecting names. If you are working alone and one or the other time is absolutely no go, then send me an email. But you really need to have a very, very convincing reason, most probably related to your other studies at the university, to be allowed to skip the other seminar event. But in any case, your team needs to be presented on the seminars, so you need to be locally present. So that's that. That's the last of these theory lectures. If you have problems, I have the consulting hours on Wednesdays from 1 p.m. to 3 p.m. And if nothing else, then we will see in 2 weeks at the seminar presentations, and we will have the concluding lecture event on 3 weeks, and then there's only exam, and this course has ended. But for now, thank you for listening, and if there's any problems, come visit me on my consulting hour or send an email to ask for further instructions. Thank you, and have a nice rest of the day.